Hey y'all, we are Memphis University and we're back for another Calculus Done Wrong lesson where we run calculus before calculus wrongs us. Today we are going to be doing a special limit topic. We are going to be talking about the squeeze theorem. So the squeeze theorem isn't found on every single AP exam. It is actually a rare technique to do limits, but it's still nice to be able to know how to do it because it allows us to take some strange limits. Basically, we're going to have some functions that involve trig at infinity or negative infinity. And because sine and cosine aren't defined at infinity or negative infinity because it just keeps oscillating back and forth, it seems like we wouldn't be able to find any limit involving that construction, but we will be able to do that using the squeeze theorem. So that's going to be our goal here, introduce the squeeze theorem and then practice with examples. To introduce the squeeze theorem, the best thing probably is just to draw a picture. So that's what we're going to do now. So let's talk about the squeeze theorem. So squeeze theorem. So what it says is that you have this picture right here. You're going to have one function called h of x. Let's write it like this. You're going to have one function called g of x. Let's make this like this. And then basically you're going to have a middle function. So that's why it's called the squeeze theorem, because you have h of x and g of x and you're going to squeeze another function in between it. So in this case, we're going to have f of x. Let's say it looks like this. That's squeezed in between here. Hopefully you can tell that that's squeezed in between here. So think about this basically as a sandwich maybe. H of x and g of x are your two slices of bread. H of x is your meat in the middle, so you're squeezing that meat in the middle. So what it says is that if you have an inequality, which is that g of x is less than or equal to f of x, which is less than or equal to h of x, and that's this picture right here. G is below f, below h. So the actual theorem says if this is true, if g of x is less than f of x, which is less than h of x, and the limit of the two outer functions is equal to the same thing. So the limit as x goes to a, so let's call this number a. The limit as x goes to a is this y value right here of h of x is equal to the limit of x goes to a of g of x. And let's say that this limit is equal to the number L. That means that the limit that we care about, the limit of the function, the middle function, f of x, there's only one choice that limit can be, and it's L itself as well. So basically, because f of x is squeezed in between g of x and h of x, and if h is going to L, and if g is going to L, that means that the squeezed function, because it's squeezed in the middle, has to be going to L as well. So that means that the limit as x goes to a of f of x is equal to L. So this is the squeeze theorem. Again, it makes a lot of sense. If you squeeze something and you're basically touching, there's no really space to be going except that where those two functions meet in contact, because there's no space in between them. So that's why we call it the squeeze theorem. So hopefully you've written down the squeeze theorem, but the best way to practice the squeeze theorem is of course with examples. So let's do some examples. So let me erase this. Let's start off with a pretty basic example, and then we're going to try to use the squeeze theorem with those trig functions. So the first basic example is, suppose we have 3x minus 2 is less than or equal to, let's say, f of x. And I believe I want x squared minus x plus 2. And what we're going to do is we're going to try to find the limit as x goes to 2 of f of x. So because we don't have a lot of information about f of x, we're going to have to use the squeeze theorem. And what we have to hope is that when we take the limit as x goes to 2 of this left function, and we take the limit as x goes to 2 of this right function, it's the same number, which forces the limit as x goes to 2 of our function f of x, the one we want, to be that same number. Keeping in mind, if you wanted to draw a picture of this, which I'm not going to do, basically we have a nice little line here. We have a parabola, and this function, which is mysterious, goes in between the line and the parabola. But again, how the squeeze theorem works, it only works in certain scenarios, but these scenarios do arise fairly often. Basically, if you have these inequalities and you take the limit and you have to take the limit, you have to get the situation where they're the same number. And if they are the same number, then you'd be able to evaluate this limit. So let's try to find the limit as x goes to 2 of this, the limit as x goes to 2 of this, and let's verify what we get. So these are going to be pretty easy limits by their construction. Notice that these two functions are continuous. So if you remember from our continuous and limit video, continuous means that the limit of the function equals the function value. So all you have to do is plug in the number. So we have this and we have this. they should be not too bad to find because all we're going to do is plug in the number. So let's see what happens when you plug in 2. Well, when you plug in 2 here, it's going to be 6 minus 2, that is 4. Then when you plug in 2 here, you're going to get 4 minus 2 plus 2, that is also 4. So this is perfectly the situation that we want. We need these numbers to match, and we need our function to be in between these other functions, and that's the squeeze theorem. So for example, this answer is going to be 4 because the limit of the left one, thus the underneath function, is equal to the limit of the above one, the right function. And we know that this middle f of x function is in the middle of these two guys, and because they're squeezed at this point, x equals 2, going both towards 4, and because they're in between, it has to be that f of x is also going to 4. So that's that limit. And that's how the squeeze theorem works. So hopefully you understand. You have these sort of inequalities. You find the limit of the outer parts of the inequalities, the smallest thing and the biggest thing. And if they're the same number, which in this case they will be the same number, and often you'll see that the answer will be 0, that means that the middle limit has to be 0 as well. So let's try to do these with questions about functions that are explicitly defined with sines and cosines, as promised at the beginning of the video. So I'm going to erase this. I'm going to erase this. Let's try to do a limit. So the limit I'm going to try to do right now is the limit as x goes to 0, x squared times sine of 5 over x. So if you do this limit like our normal limit ways, it's going to be hard to do this limit because when you plug in 0, over here the 0 is okay, 0 squared is 0. But when you plug in 0 in here, well, 5 over 0, that's going to be infinity or negative infinity. We should put a plus here just to do the right side of infinity, just to be more careful. So when you plug in this 0, it's 5 over infinity. 5 over 0, sorry, it's 5 over a very small number. Remember our limits involving infinity video. But 5 over a very small number is a huge number, it's infinity. But the problem is that we're not going to be able to find the sign of that because notice that sign oscillates back and forth, and because this quantity isn't a number, it's just going to keep going back and forth, even as it approaches infinity. So it seems like we can't do this limit because it's 0 times some undefined quantity, so I don't know what that is. But we can use the squeeze theorem. Keep in mind that when we introduce the squeeze theorem, it would have 3 functions, a less than, the middle function, and a greater one. So we have to introduce inequalities somehow. And the way that the squeeze theorem works, usually with these trig functions, is using a set of inequalities that come from the definition of trig functions. So mainly we're going to be working with sines and cosines today. Keep in mind that sine and cosine are always between -1 and 1. If you look at the graph of sine and cosine, it always oscillates where it never goes above the line 1, never goes below the line -1. Another way to think about this is that on the unit circle, sine of x is the y value of any angle, and the smallest y value you can be is -1. The biggest one you can be is 1. Same thing with cosine. So what I like to do is I like to introduce inequalities again based off those trig rules. So we're going to have -1 less than sine of anything. So it's less than or equal to 1. So whatever is in the sign, I don't even know what this sign is. Again, it keeps oscillating back and forth, so it's actually not a number. But we know that no matter what happens, sine of whatever is in the parentheses will remain between -1 and 1. So what you do next is you're careful with maintaining inequality rules, but all you have to do is go from here to eventually arrive where the middle thing is equal to this original limit. So all we have to do actually is multiply everything by x squared, and we should be good to go. So notice that'll be -x squared less than or equal to x squared times sine of 5 over x. And then finally, this is going to be x squared. Again, all we did was multiply every single one of these pieces by x squared. And because we have a positive thing, because x squared is positive, we don't have to change the inequality. So we have this. And notice that when we have this, finally we can employ the squeeze theorem. So what we're going to do is we're going to find the limit of this, we're going to find the limit of this, hope that they're the same, and that makes this final limit equal to whatever the number is if they are the same. But notice that they are the same because when you take the limit as x goes to 0 plus of -x squared, that's going to be equal to 0. Same thing with the limit of this guy right here. That's also going to be equal to 0 because when you plug in 0 here, 0 squared or negative 0 squared are both 0. So that means that this limit, because this function is squeezed by this this bottom function and this top function, that means that if their limits are the same, this original limit has to be that same number. So in this case, the answer is 0. And you're going to see that 0 is often the answer to these questions because it's easiest to squeeze at 0. But again, this is the squeeze theorem. Smallest thing, middle thing, big thing. How you have to start the question is introduce a trig function yourself. So in this case, we introduced where sine of 5 over x, we have the sine of whatever thing is in between -1 and 1, and then we sort of did our work here. We multiplied everything by x squared so that the middle thing matches our limit, and then we hope and pray that the limit of the outer two things are equal to each other so that the limit of the middle thing is squeezed, so it has to also match that limit. So in this case, because both of these limits are equal to 0, that means that our middle limit has to be 0 as well. And that's how the squeeze theorem works. I know it's not super exciting, but again, it's the same thing over and over again. Some students like to do this because often the answer is 0. And let's try to do another question where the answer is 0. So let me erase this real quick. So let's erase this. Let's erase this. And now let's do another limit. So what we're going to do is we're going to do the limit of e cosine of x over, let's not do x, let's do 2 over x. Maybe x squared just to make things a little bit spicier. We're going to do the limit as x goes to 0 again. And we're going to do the square root of x because we want to have positive things. So this is my next limit. So again, you can imagine that this is going to be squeeze theorem. We're not able to just plug in the number, unfortunately, because when you plug in 0 into the bottom, you're going to get 2 over 0, 2 over 0. My 7th grade teacher taught me that 2 over 0 you can't find because the bubble pops. Boom, 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 pop. 2 over 0. So cosine of infinity is not defined. It goes on forever, so it oscillates between 1 and -1, so it's not a single number. So we do have to employ the squeeze theorem, and hopefully the squeeze theorem will allow us to find the answer. Just like the previous one, what I like to do is I always like to start off with sine or cosine of whatever's in the parentheses is in between -1 and 1. So in this case, I'm going to write cosine of 2 over x squared is in between 1 and -1. And this is again because sine or cosine of anything is in between -1 and 1 because of the unit circle or because of graphs of sine and cosine. Then what you do is you need to slowly do algebraic steps, being careful you don't change the inequalities so that you match this middle thing. So how am I going to go from this to this? Well, it looks like I need 2 steps. First, I'm going to raise each thing to the e, and that's perfectly fine because e is always increasing. So if you're smaller than something else, then e to that thing is smaller than e to the bigger thing. So in this case, we're going to raise everything to the e to the -1, e to whatever cosine thing. And then finally, it's going to be e to the 1. So it looks like we haven't reached our original limit, and that's going to be our ultimate goal, of course. So what I have to do is it looks like I have to multiply everything by square root of x, but it shouldn't be too bad, so I'm going to do that. So it's going to be everything is going to be multiplied by the square root of x. So square root of x times e to the -1. Then it's going to be square root of x times e to the cosine of 2 over x squared. Look how beautiful this is. This is exactly what we want. So it looks like we're doing the right thing. Finally, on the right side, you're going to get square root of x times e to the 1. So again, this question was a little bit harder than last question because it would involve 2 steps to get to the thing we want. We raised everything to the e first of all, and then finally we multiply by square root of x. Now it's time to hope and pray. Because we hit that middle thing, what we're going to do is we're going to take this limit of x as x goes to 0, and then we're going to take this limit as x goes to 0 and see what happens. We're going to hope and hope and hope and hope and hope that they're the same number, because if they're the same number, that means we're done. So in this case, we're going to do the limit over here because I'm sort of unorganized my work. I'm going to do this limit over here. It's going to be square root of x times e to the -1. So as x goes to 0, then you're going to have the square root of 0. That's just 0, of course. E to the -1 is still a constant number. It's just 1 over e, and 1 over e is like 1 over 2.7-ish. So when you have a constant number, a finite constant number, multiplying by 0, what is this limit? Well, it's going to be 0, of course. Then, same thing over here. When you take this limit, it's going to be the limit. We can write it a little bit sideways. The limit as x goes to 0, whatever number you're going towards, square root of x. We're going to put a little plus here to make sure we're not plugging in negative numbers into the square root. Square root of x times e to the 1. Well, again, e is 2.7. When you multiply that by 0, which is where the square root of x is going, because you're plugging in 0, square root of 0 is 0, then this will also be 0. So finally, looks like we have the situation we want. Our middle thing is in between two guys, where when you take the limit of both of these guys, it's the same number, which happens to be 0. So finally, what's this answer? Looks like we are going to have 0 as the final answer. So that's the squeeze theorem. Constructing an inequality, eventually getting to the function you care about, where the function you care about is in the middle of the inequality, and finally taking the limit of both sides and hoping and praying, but probably your wishes will come true that the limits of both sides will be equal to 0. So let's see that we can employ this strategy even if we're going to infinity instead, as opposed to 0. So let's do 2 more questions. So I'm going to erase this. Hopefully you had a time to write it down. Of course, we have technology where if you didn't, you can just pause the video and rewind. But I'm pretty excited. I'm going to finish this lesson out. Let's get started. So we're going to do the limit as x goes to infinity. And we're going to do, let's say, cosine of x over x squared. So this is my next question. Again, hopefully you've seen our limits involving infinity video. I don't really remember if it comes before this video or after this video. But when we talk about limits as x goes to infinity, basically we're just saying we're letting x get bigger and bigger and bigger. X going to infinity, infinity isn't a number, but what we're saying is we're going to plug in 1,000,000, then we're going to plug in 1,000,000,000, then we're going to plug in 1,000,000,000,000, and so on. And the main way to do these limits are same heavy, top heavy, bottom heavy. Go watch our limits involving infinity video if you want more practice with this. The problem though is that when we plug in infinity, we get cosine of infinity. And again, you can't do cosine of infinity because again, cosine keeps oscillating back and forth, back and forth, back and forth, back and forth, just like this. It won't stabilize at a single number, so the limit doesn't exist. We can still find the limit of this entire fraction though, because of squeeze theorem. So how it works is, just like normal, we're going to squeeze it in between cosine of x between 1 and -1. You have to introduce inequalities in order to use the squeeze theorem, because you need something smaller than something else, which is smaller than that, the biggest thing, I guess. And the way we introduce inequalities, again, is using the fact that the cosine of x, meaning the range of the function, I believe is the right word, is in between -1 and 1. Finally, you have to get to whatever step you need to go, but notice that it's going to be pretty easy. All we're going to do is divide everything by x squared. So we're going to divide everything by x squared, divide everything by x squared, divide everything by x squared. So now what we're going to do is we're going to hope and pray that when we plug in infinity into these two limits, another way to say this is that we're going to take the limit as x approaches infinity of both the outer things. We're going to hope it's the same number. It is going to be the same number. It's going to be 0, just like it always is. But once they are the same number, that means that my final limit will be the same number. So on the side here, we're going to do this limit right here. -1 over x squared. So we can use the squeeze theorem even if we're going to infinity and not a finite number. When you plug in infinity here, it's going to be -1 over infinity. That's just saying you have -1 and you're splitting it up amongst an infinite number of things. So just imagine you have -1, you split it up amongst 1,000,000 things, 1,000,000,000 things, 1,000,000,000,000 things. Every single person is going to get an individually smaller piece until eventually you get 0. So in this case, this answer is 0. Same thing with this limit right here. We call this bottom heavy because x squared is on the bottom. There's no x's on the top. And anytime anything is bottom heavy, the answer is going to be 0. Again, if you need to think about this, think of a candy bar. Think about splitting up the candy bar amongst 1,000,000,000 things. Every single person will get such a small piece. And if you split it up amongst 1,000,000,000,000 people, this piece gets infinitely small until it's basically 0. So that's why this limit is 0. And these two limits matching is a perfect scenario because we have this bounded in between two different things. So it looks like our final answer, of course, is going to be 0. So let's try to do another one where it's going to be very similar to this. We're going to do this process, but we might not actually get 0 for an answer, and that's always exciting. So let's keep going. So I'm going to erase this. Let's do one final limit. And we might have done this limit differently in the limits involving infinity video. I'm not sure if that's going to come before or after, but let's do this one. So this is my function right here. Again, if I plug in infinity, I get sine of infinity that's undefined. I start panicking. I want to find this limit, but it seems like I can't find this limit because I get sine of infinity. But don't worry, we have Squeeze Theorem as a tool. So what we're going to do is we're going to do Squeeze Theorem and we're going to see what limit we get. So in this case, it looks like we need to have limit as, just like in the previous examples, we start off with sine of x being between -1 and 1. So sine of x is in between -1 and 1. Then we have to get to this right side. So it looks like we have to first add 5x and then we'll divide by x in order to get to this middle thing being the original function. So first off, again, I'm going to add 5x to everything. So it looks like it's going to be 5x minus 1. Then it's going to be 5x plus sine x. Finally, on the outside, it's going to be 5x plus 1. Then we do need to get to that middle, this middle thing. We need it to match the original function. We are so close, just so close. We have 5x plus sine x. Looks like we have to divide everything by x. So we're going to divide everything by x. And lo and behold, we have reached our sort of the halfway point. We have gotten this middle thing to match this limit, and this middle thing is bounded by two other guys. So our goal is to find the limit of both of these things and hope that they're the same number, and that'll be our answer. So let's do that. So what we're going to do is we're going to find the limit as x goes to infinity of 5x minus 1 over x. Then we're going to take the limit as x goes to infinity, 5x plus 1 over x. Hope and pray that they're the same number, because if they're the same number, that means my middle limit, which was squeezed in between these two outer things, will be the answer. And if you watched our limits involving infinity video, whether that be in the future or in the past, you'll know that this limit is called same heavy, because as you're going to infinity or negative infinity, you compare the leading exponents of the numerator and the denominator. In this case, they're both 1, x to the 1, x to the 1. And same heavy, the answer is just the ratio of those leading coefficients. So this one is just 5. Another way to think about this is as x goes to infinity, like a billion, trillion, quadrillion, this subtraction 1 won't do very much. A billion and a billion minus 1 is a very similar number. A trillion and a trillion minus 1 is even more similar. So in this case, when you do the minus 1 really doesn't matter. So you're left with just 5x over x, which is just 5. Same thing in this case. The plus 1 doesn't matter. This is same heavy as well. This is going to be 5. So we have the final answer, not 0 this time because we have something same heavy, unlike our previous example, which was bottom heavy. Because these two outer limits are both 5, and because we squeeze this function in between our two functions, looks like our final answer is going to be the lovely number 5. But that's how the Squeeze Theorem works. Hopefully these 4 to 5 examples of the Squeeze Theorem allow you to sort of master the Squeeze Theorem, or at least provide you a base of the Squeeze Theorem. If you want to master the Squeeze Theorem, we have a Girls Teach Calculus video that I'll link in the description of this video, where one of my former students practices a lot of these Squeeze Theorem questions. She has a lot of questions involving trig, where the answers are usually 0, but she introduces Squeeze Theorem as well. You might think that she explains things better than me, so be on the lookout for that. Hopefully you are sort of continuing on with us as we finish this limit unit. Eventually we're going to introduce derivatives, which is the most important part about calculus, where derivatives are inherently a limit, a special kind of limit. So hopefully you'll watch that video. Whatever video you choose to watch, we are very happy and very appreciative of you watching this video. Give us a like and subscribe if this video was useful for you. Whatever you choose to do and whenever we will meet next, I will look forward towards that day. Don't know what I'm talking about anymore. Thanks again for watching just like normal, and I hope to see you next time, whenever that next time is. Thanks again.